University, where Sir was, I think, one of the directors.
He's back in he's in Dhaka nowadays.
He's in Dhaka, sir. Yes. But I think he travels to Singapore and US quite regularly, I think.
Yes.
Sir. So I met him this January. I was in Dhaka for this Indian Ocean Summit. So Sir was also part of that. So we'll start another 5 minutes, sir. 4 o'clock.
Okay.
Yes.
Where is this company Nirdhwani located? Delhi.
It's mine only, sir. Pune only, sir. Pune only.
Acha, your one. Okay. Sonar, basically. That must be Sonar, no?
No, sir. All the innovations and field validation, field deployment, turnkey projects will be done by NDT, and MRC is a not-for-profit. We look at policy and basic research. Sir. So both of them work together to progress the underwater domain awareness.
Correct.
So we'll be now training some of the US Department of Defense, Navy, Coast Guard, Marines in Bangkok in September, sir. So they find value in the UDA framework. So I've been invited. And also Institute for Maritime Policy and Strategy based in Haifa has invited us in November to present the UDA framework that we have built. So today my colleague Sridhar will be presenting the actual technology platform that we have built. So you get a better sense, and then the presentations following that will cover how those smaller components are being stitched together, sir.
Okay, very good.
So now it's a more ready platform for deployment. So it makes more sense now that one can even look at how things can be, even policy, I mean, data-driven policy now can be easily looked at. I mean, policymakers now will have real data to build their policy. I mean, what would be the impact of climate change in the next 10 years, 15 years, 30 years? So if you have some identification of those issues, it becomes easier then to manage. So that's what this platform will do, sir.
Good. No, it is very useful platform.
So earlier it was more, I mean, on paper, but now there is an actual platform that has been built and which can be actually demonstrated. So that's what we are going to now start doing. So our publication on the marine spatial planning is also now ready. So Springer Nature is going to come out with that in next 2-3 months. So I just had a word with them. So they are sending it for the final editing, and so another 6 weeks it should be ready, sir. Mudgal sir is one of the co-authors.
Marine spatial planning is a key thing nowadays, you know, is a key, and that I think government will require that data.
Yes. So, I mean, what we're doing is, sir, one is the handbook comes out with the entire what should be the policy framework and how it has to be driven. And parallelly, what you will witness today is the actual digital platform which we have built. So both of them together will be the real thing on the ground.
So how much planning have we done so far in India, marine spatial planning?
Very little, sir, because I mean, it's a very, firstly, it's a very vast topic and vast subject. I mean, for us also, after having spent so much time, our understanding has also become, but it has so many different dimensions. Marine fouling is different. Deep sea mining is different. Coastal mining is different. Connectivity is different. Then freshwater, we are looking at inland water transport. Then they are all interconnected. I mean, you try to solve the fisheries problem, you'll have problems in the ports or vice versa. So how do we interconnect? So now having a digital platform, it will be easier for us to interconnect. And so, I mean, policy is always a trade-off. So how will you do that trade-off? So it has to be data-driven. So that's what we are trying to kind of build, sir.
You know, about 3 years ago,
Sir,
um, Navy Chief
sir,
Admiral Karambir Singh, he
sir,
had addressed our society,
sir. Yes,
and he has spoken on marine spatial planning.
yes, sir. Yes, sir.
I think that address, I think it is on YouTube.
Okay, sir. Okay, sir.
You can have a look at that, because
Certainly,
he
sir.
was
Yes,
serving Navy Chief, and
sir.
he had taken particular interest in this subject, and he had
Sir,
spoken specifically on it. Uh,
sir.
so I think that, of course, now already 3 years old, so much has probably happened after that, but still, it
No,
needs this kind of.
sir is deeply involved. I mean, in the underwater space also. I mean, he
Hmm,
keeps talking internationally also, and he has also written.
I
We have
see.
compiled a edited volume where 10 authors have contributed. So Admiral KB sir is also one of them, and then we
Okay,
have
okay.
many
Then, of
US
course,
Department
yeah,
of Defense think tank heads
yeah.
also who have and plus our own
Okay,
authors. So
I see, I see. Hmm.
we'll start, sir. Nishtab, over to you.
Yes, thank you so much, sir. So good evening to everyone present here, especially to the researchers, the interns, the guest with us. Thank you so much for joining us online. And on behalf of the Maritime Research Centre and Nirdhwani Technology, it is my great pleasure to welcome you all to the final presentations of the 2026 UDA Summer Internship Programme, featuring interns from IIT Bombay, IIT Delhi, IIT Madras, and IIT Kanpur. Today's event marks the culmination of several weeks of intensive research, innovative research work, collaborations, and mentorship. Throughout this internship, our students have worked to solve the complex challenges spanning topics including marine spatial planning, sediment management, underwater acoustics, biofouling management, fisheries, climate resilience, and many more domains that contribute to the overall picture of UDA framework. So some housekeeping, messages for everyone. Kindly ensure that your microphones are muted through the session. We encourage you to post your questions in the chat box if you have any, so that we can take them up in the discussion round. The session is being live streamed on YouTube and recorded for the documentation purposes. And today's presentations are not merely the project reviews. I feel it's a celebration of the curiosity, scientific inquiry in the next generation of underwater and maritime researchers. So without further delay, let's begin today's program. It is my privilege to invite the founder and director of Maritime Research Centre, Dr. Commander Arnab Das, to deliver the welcome remarks and formally inaugurate today's workshop. Over to you, sir.
Thank you, Nishtab. First of all, I'm extremely grateful to our esteemed panelist. Ambassador Devre sir has joined. Others, I'm sure, will be joining very soon. Ambassador Tariq Karim from Bangladesh, Dr. Hussain from Maldives, and Rear Admiral Jairatne sir from Sri Lanka. Very eminent panel. Today, as Nishta said, it is just not a project presentation. It is also showcasing the importance of the underwater domain, the diversity of the underwater domain, and the complexities of the underwater domain. And this is the culmination of one batch of interns. We had 36 interns this season, this summer at MRC, all from very premier institutes, IITs, top five IITs, BITS Pilani, and also St. Stephens. So, BITS Pilani students were with us physically at our center for 8 weeks. Their final presentation was held on 15th. St. Stephen's students joined us a little later than the others. So, their final presentation will be done on 9th of August. And today, our 12 interns from the top four IITs are presenting, and you will see a diversity of projects. And so it's a very structured program for us. These interns do a very meticulous work, guided, of course, by our mentors. And our mentors are also coming from the same set of people. So some of them may stay back with us as mentors. And so each of them are focusing, each mentor focuses on a specific topic. Somebody is looking at fisheries, somebody is looking at aquaculture, somebody is looking at biofouling, somebody is looking at the sonar performance, or somebody look. So there are different mentors looking at different areas, and they have themselves spent few years looking at that subject, and they have a significant body of work themselves. And so our in the last couple of years, our internship has taken a very different and everybody is solving a real world problem. It is not a theoretical discussion. It is not imaginary discussion. They are identifying a real world problem and they are trying to solve a real world problem. So I think I will stop here and I will hand it over to Sridhar to present the broader MSP platform. As I was mentioning to Ambassador Devre sir, we have completed a MSP handbook, which largely, I mean, which has been authored by Catherine, my colleague, and also Ambassador Mudgal sir has been one of the co-authors in that. That covers the larger policy side of it, but Sridhar is going to present the actual digital platform that we have built. Over to you, Sridhar.
Thank you so much, sir, and thank you everyone for joining today. I think it was great context to be set around the importance of marine spatial planning as it was as discussion was happening now. So what I'm about to present today is our tool that we're building on modeling and simulation based marine spatial planning. It's a AI driven approach. Specifically speaking, it's a physics informed AI machine learning model that we essentially incorporate into the traditional marine spatial planning aspect. Now, why physics involved? Because standard AI that has been existing for quite some time learns entirely based upon historical data. So essentially presence of marine mammals in a certain region or presence of, I mean, whatever data we could capture, that training our model on top of that is what yields the result. But we know for a fact that ocean is extremely dynamic in nature and noisy and extremely unpredictable. And therefore, collection of data in itself is a very sparse and often a very extremely expensive effort per se. And this is where the standard AI fails. This is where the physics informed AI comes into picture. What we essentially mean by physics informed AI is the AI is trained on the mathematical equations such as the fluid dynamics or the equations for the acoustic waves or the thermodynamics and so on. So the brain of the AI, as such, what it computes is physics informed. It understands the reality of the situation. It understands how waves propagate. It understands how. So it's not just a match of capturing what the historical data is and predicting out of that, but rather coming up with a mathematical equation that it tries to solve. Now, before I get into what we are actually building, I think it is extremely important to understand what we are solving for. Now, MSP is not a new concept. It was established in 1980s under the when the project for Great Barrier Reef was established in Australia. It was again, of course, it had a different naming back then, but the core concept remained to be zoning of the region. So zoning of the region so that agencies or stakeholders can utilize it. So by that, what we mean is that if we have the ocean environment, we zone it into what areas can be utilized for wind farms, which areas can be utilized for marine mammal habitat, and so on and so forth, based upon the different properties those areas have. Uh, but traditional MSP and the same practice which has been followed for quite some time now, it essentially relies on extremely isolated set of data sets and multiple agencies coming together to provide that data set. And both in India as well as globally, there has been a issue or there has been a problem of fragmented data. So we have multiple agencies which are collecting data, we have multiple agencies which are collecting different forms of data. A CWC will collect a different form of data, MOES will collect a different form of data, but there's not a single platform where all of that can be put together and it can be analyzed to yield an outcome. And that's what has also been represented in the World Bank report from 2020. If we look at two of the examples of how this actually impacts, in Tamil Nadu, again near the in Tamil Nadu, off the coastline in Dhanushkodi, there were sea walls being installed to prevent local erosion. But the construction of sea walls for prevention of local erosion did not take into consideration how the sediment essentially flows seasonally. So what ended up happening is that that localized fix for that particular region ended up just shifting the problem downshore to a different area, and the adjacent fishing villages lost their beaches, all the turtle nesting in the region have declined, and so on and so forth. And this was being brought out, and again, critics have noted that this is essentially a siloed fix which did not take into account how the sediment flows, how the water flows. Another good example would basically be the Kerala project. We know that the Biringam project was established, a 900 million transshipment hub, which was established without taking into account how construction would affect the local fishing communities. And we know that by 2018, it essentially saw a mass amount of protests that were erupted because, again, the fishermen were essentially identifying that they lost their fishing hamlet by this particular process or this particular project. Now, it was not that the initiative was not planned enough, but the problem was the lack of information or the lack of a single platform where we could predict what the future is going to be. And that's what our modeling and simulation based marine spatial planning brings into picture, which is dynamism and impact modeling. So we wanted to build a tool which essentially continuously adapts to the changing marine environment. So we can essentially see that if we were to provide a particular set of if there's an increase in sea level rise today, then how does that impact the coastal flooding tomorrow? So that kind of dynamism, to be able to adapt to the real-time data, was one thing. And the second thing is the impact modeling. So forecasting of different actions, different scenarios, identifying what if scenarios. So essentially, if I have a shipping noise that is being generated, then if I change my shipping route, then how is that noise going to differ in the ocean environment? How is that? And then if by changing the shipping route, and if I can see there's a change in the distribution of the overall ocean noise, then can I then better account for the marine mammal habitat? So such kind of questions can easily be answered by such a predictive mapping tool. And that's why we are essentially shifting from being reactive to being proactive with this particular tool. Now, the overall architecture of how we are going about it, the first and the foremost, the most important layer essentially includes the real-time historical data. This includes the oceanographic data, biodiversity information, AIS traffic. So we ingest all kinds of information and across various different streams. All of that is basically pushed into simulation engine. And as I mentioned, this is where the physics informed modeling comes into picture, where we build a hydrodynamic model to understand how the water flows. That then goes into impact analysis and scenario testing, where stakeholders can identify different scenarios. If there's an increase in sea level rise, then if we take the cyclone Sidr or cyclone Amphan that happened a couple of years ago, now if we want to replay the same event 10 years down the line or 15 years down the line with an increased sea level water or an additional amount of rain, then how would that impact the urban as well as the cropland area in the region? So that kind of an impact analysis is something that this tool provides. And of course, a decision support interface, because it's extremely important that with all of the simulation and all of the modeling and data that we are providing, it is important for stakeholders to be able to use that for making policy. So a decision support interface that essentially provides them all the information that they need. That's what we are building. So this is the MSP tool that we have built. This, as you can see on the left-hand side, there are planning layers. A stakeholder can select from the different planning layers. And on the right, these essentially represent the 6 different initiatives that we have, or 6 different domains that we are covering under the MSP. The underwater noise mapping, the coastal and riverine flood risk analysis, oil spill drift simulation, marine biodiversity and habitat suitability, and so on. I'll explain in depth what each of these essentially mean. But an important aspect to consider here is that we are not just, so the key of the MSP tool that we are building is that we are not just essentially putting AIS data on a map and saying that these are where the vessels are situated. What we are doing is we are calculating the noise that this ship is generating. So for example, in this one, you can see that if you hover over a particular dot, each of those dots represent the ships in the Indian Ocean. You can see what is the ship, with what speed it is moving. But more importantly, the color coding represents the noise that is being generated from the ship. So it's not just about putting there a static map of data, but rather calculating calculating an attribute of interest. So that's one example. But broadly speaking, the first initiative of underwater noise mapping essentially covers modeling the acoustic environment for the complete Indian Ocean region. Now, if we talk about the India's ocean noise floor in general, there are two major natural contributions that happen. One is wind-driven noise, which is basically caused by wave breaking, and also the rainfall impact, apart from the shipping noise. And both of all the three of these are extremely significant in IOR because of the diurnal and seasonal changes that we have in the environment. And we have extremely high rains. We have monsoon that happens across the region. Now, what we do is we model these natural as well as the anthropogenic sources, apply a propagation correction model, as in we construct a channel model that essentially drives how acoustic propagation happens for the signals. We provide to it the environmental factors that impact the propagation of these signals, so the bathymetry, the sound speed profile, and all those things. And that overall gives us the cumulative acoustic stress map. And that's the first module that we have delivered for the this thing. And in fact, a lot of presentations that you'll be witnessing today essentially covers some of these different topics. I mean, so a large amount of work has already happened in this MSP initiative, while we are continuously adding more and more elements, and the presentations that we'll be seeing today contribute to the MSP initiative in some or the other way. The second initiative is for the flood risk. So there are two distinct flooding mechanisms. Again, rivers overflowing from any kind of upstream rainfall, as well as the storm surge, essentially that pushes seawater inland during cyclones. And when they coincide, that is when and this is something that happens in Ganga Brahmaputra Delta quite often. The result is dramatically much more worse than what either of them can, either of the catastrophic failures that either of them can alone provide. So this compound flooding is basically a dominant failure mode that we have seen across and throughout the history, and the traditional MSP does not model or account for it. So we basically build separate models for riverine and coastal search, and then combine them using the joint probability analysis. And this is where again the scenario testing comes into picture, that now you provide a data of a higher sea level rise. So the hydrodynamic model can essentially take into account how the higher sea level rise is going to impact the overall flooding. And that's what I mentioned by saying that we can replay the scenario of what it's going to do in the next 5 years, 10 years, or 20 years down the line. The third initiative we are working on is coral bleaching and risk forecasting. Now, we know that coral bleaching occurs when sea surface temperature exceeds the local historical maximum by a certain range. But temperature alone is not a factor, is not a driving factor. If we consider just the temperature as an aspect, it generally overpredicts where the corals have adapted. Now, what we essentially then do is we take into account the other factors. So we created a multi-stressor framework here, which includes aspects such as acidification, turbidity, nutrient loading. All of those are getting combined into identifying the thermal refugia. And what we mean by that is, if we want to conserve coral reefs, we need to first understand which regions are the least impacted and which of the regions are more sustainable for us to first put an effort towards conserving. That's what the broader outcome of this particular work is. The fourth initiative is on oil spill drift simulation. Now, this essentially includes now approximately 40% of the global seaborne oil trade passes through our basin. And this India again is a monsoon heavy region, and monsoon and waves and everything essentially shift the way an oil travels. So there are two factors that we are considering here. One is to identify an oil leakage, and second to calculate the oil drift. So where an oil leakage is happening and X hours down the line, how that oil is going to drift and spread across the ocean, and how is it going to impact? And this is where, and none of these initiatives essentially are independent. All of them talk to each other. I'll explain a bit more on that. But just to give some context, like we looked at the coral reef bleaching, we looked at the oil spill drift simulation. Now, oil spills also impact coral reefs, so they essentially talk to each other. So oil spill drift, like detection of oil spill and detection of the drift of the oil spill, how much area they're going to cover X hours down the line. They also help us inform where the coral reefs are at risk, and so on. The fifth initiative is on the blue carbon and ecosystem health, which is essentially for monitoring the mangrove, seagrass, and salt marshes. Now, these are some of the most carbon-dense ecosystems that we have on Earth, and the Indian Ocean region contains roughly 40% of the global mangrove extent. So we first initially start with an extent and change mapping. So we basically grab around 25 years of satellite data, and map out where all we have identified the mangroves and seagrasses in the region. But what the extent alone misses the degradation. So we want to also identify that what are the different factors that would combine towards the degradation of seagrasses and mangroves. And this initiative essentially is to predict that. The sixth and the final initiative is on the marine biodiversity and habitat suitability. Now, we have quite a few. This essentially is mapping the acoustic habitat for marine mammals across multiple species, blue whales, dolphins, green turtles, snapping shrimps, and all of these are operational at this point. The difference between the traditional and our version of acoustic habitat mapping here is that we do not just look at the historical data. Like ideally, the concept is that you look at historical data of where the presence of these marine mammals are present, are seen, and then you map that into the MSP layer. But the problem with that is that it is skewed by the how much a human can essentially reach out into water and identify. I mean, we essentially perform recording where we are available. It's not about where the marine mammals habitat actually is present. So what we end up doing is we identify the migratory pattern based upon the ecosystem of these marine mammals. So for example, we look at chlorophyll data, which essentially translates to the food, because chlorophyll is required for microorganisms that are in turn food for these marine mammals. And so we track from that perspective and we identify what are the different acoustic habitat for the marine mammals. Again, for snapping shrimp, that basically means that identify regions which are having higher temperature, because snapping shrimp thrive in such kind of region. Now, looking at some of the unique deliverables that we have and the modules that are live today, this tool is something that we've already built. This is the shipping noise mapping, the first initiative that I was talking about. The small dots that you can see represent the individual ship. And of course, as a user, as a stakeholder, you can, of course, zoom in, zoom out, and identify the different regions that are area of interest for you. And the larger heat map that you see represents the overall noise level ranging from 10 to 120 decibels throughout in the region. Of course, you can see the correlation between the extremely dense traffic region as well as the noise that is being generated by these ships and how they are propagating. We've also done some work on acoustic habitat mapping for blue whales, turtles, and snapping shrimps. We have done some work on potential fishing zone mapping as well. This is again live in terms of identifying the high probability fishing zones based upon the sea surface temperature and the chlorophyll data and all those different components. Again, we've seen variation in this across both quarterly as well as across 2 weeks, based upon how the monsoon is, based upon which season it is, and so on. As I was explaining, all these initiatives are connected to each other. Mangroves and Flood Risk Initiative 5 from Initiative 5 directly maps to the Initiative 2 of the storm surge. Because again, we know for a fact that the mangroves are the first line of defense for any of the flooding or any surging that essentially happens. The noise and biodiversity aspect, if you look at the what we have generated in the first initiative of underwater noise mapping, that directly goes to the marine biodiversity, because once we overlay two maps on top of each other, we can essentially see which of the region are of high noise level and which of the regions essentially are a habitat for marine mammals. And that one layering on top of each other gives us much more information than just individually these two aspects. Again, that's another advantage of what this tool that we are building. Now, why this matters for India? One is extreme variability. We have like India's coastline face some of the highest amount of climate and human activity variability. And what I mean by that is that we have fishing, we have seasonal fishing, we have festive fishing. Regardless of the season, it is more related to the festive aspects of things. The second thing essentially is the data fragmentation. Now we have a data that is being collected by a lot of different departments, but in separate silos. And as a platform, we want to bring it together in a unifying framework where the agencies can essentially push data into our platform as well as pull data from the platform. So an open model where multiple agencies can come and contribute together. The third is the resource constraints. Again, even if we were to do all of this work using like real world data or calculating the real world data, it is extremely costly. So blanket deployment of sensors for recording the data is not something that is feasible for developing nations. And the fourth essentially is the governance complexity. Today, there is no single marine special planning authority that exists for India. Tomorrow, when we essentially look at policies, tomorrow when we look at the international exposure for India as well as other countries, we want a platform which they can rely on to derive these policies, and we have built this MSP platform to be exactly for that purpose. So that's what we are envisioning by 2029, that we'll essentially have a unified simulation-driven platform. More than 50% of this is already ready, which we are launching soon. And yeah, that's pretty much my presentation for the day. Thank you.
Thank you so much, Sridhar, for giving a very comprehensive overview of the center's work and for providing the details about the diverse research opportunities that lie under the whole of the UDA framework. We now move on to the most anticipated segment of today's program, which is the final presentations that our interns from different IITs are going to present. So each intern will have approximately 5 minutes to present their work. So we begin with group 1, focusing on marine spatial planning, which is an area that it integrates environmental intelligence, climate science, marine ecosystem, and underwater technologies for better ocean governance. So we have with us the first presenter, Devraj Karan Singh from IIT Madras.
Yeah, thank you so much, ma'am. So I am Devraj Singh. I am a BTech third year aerospace engineering student at IIT Madras. So the project assigned to me was the river and flood module for the tropical major basins, where we will be focusing mainly on the five basin deltas, namely Mahanadi, Godavari, Krishna, Irrawaddy, and Ganga Brahmaputra Delta. So these tropical deltas face some of the unique challenges that are present that are different in the temperate regions, such as extreme monsoons and the climate variability that can make them very flood-prone regions that are present there in the Asia. So what our flood module will try to achieve is finding how deep the flood will be and what will be the extent of the flood for a given discharge. So to design a flood module, we need few parameters to start with. So the first parameter that we'll be needing is a digital elevation model. So for this project, we use the FEPDAM, which basically removes the forest and buildings out of it, because we can't directly use the satellite data, as the water flow will be determined by the surface that is present there and its elevation. The second thing we will need is the width of the river. So for that we are using the GRWL data sets that is there, that will give us the river center line and the width of the river. Now combining these two will form the backbone of the bathymetry that we'll get. Now third thing we'll need is the water discharge and the input points where we want to make the water inflow. So for that we need some boundary condition that we can get using the historical data sets. For that we are using the GLOFAST historical data set for last 20 years. What are the water discharge present in these rivers? And fourth, of course, we have our model, list flood model, which is the physics-based model for water flow. So to start with, we need to get the boundary conditions. So using the last 20 years of the data set, we'll extract out the three discharge values, namely Q10, Q50, and Q100, which will basically give Q10 is basically the discharge value above which there's only 10% chances that water discharge will go above it. So if to give an example, here are some values. So if we have 28,000 Q10 for Mahanadi, then there are just 10% chances that the water discharge will go above it. Q50 means 2%, so there's just 2% chances that water discharge will go above it. And Q100 means only 1% chances. So this is like the rarest of the rare flood that might occur once in 100 years. So these are some of the flooding parameters, initial parameters that we started with. Right. So as I said, we have downloaded a data set that gave us the river width. But the biggest problem that we face is that to design the river bathymetry, we need the depth of the river that we don't have. There's no open data set available that can directly give us the depth of the river. So to go about this problem, we need to carve out our existing digital elevation model to get the right depth. Now we can't get the precise depth, but there are some few research paper available that gives us some formulas that relates the width and the depth of the river. So using the width data set that we already have, we calculate the depth of our river and then carve it out of the digital elevation model to get the final bathymetry. So these are some of the steps that we follow on our existing digital elevation model. So it's like going about finding the imposing the width on the digital elevation model and finding the depth, and from each point carving it out, carving that much of reducing the elevation at those points to get the right bathymetry that we need. Right. Oh, for the last step, we need a few files to start with. For example, first we need to define what are going to be our water discharge. So we have found we are going to perform it on these three values for the 5 deltas. And next thing we'll need are the input points where we want to make the water inflow. So that we need to give in this some of these files, so-called .bci file, where give the coordinates of our points where we want the water to inflow. And then we compile this all together and execute the list flood model on this. So if I can just show you an example, this is the Q10 simulation that I did. Each stamp is showing 12 hours. So we can make it simulation even better if we change the timestamp, but then it will take a lot of time to perform each data set. That's why I perform it like day wise, 24 each varies for 24 hours. So this is Q10 for Ganga Brahmaputra Delta. After performing these on the other river also, here are some results that we got. Before directly putting that on the map, we have to do a little bit of filtering, removing, for example, 0.05 meter, because even the small values will be shaded in the purple region that might show that it's flooded, but actually the water level is just so minute, or maybe some error here and there, that it is insignificant. So removing those small values, this is the final result that we got for Godavari. So the first one is Godavari Q10, which is like the 90% probability discharge. Second is Q50 and fourth is Q100. Now, as you can see, the flooding region increases as we go towards Q100 because the water charges decreases, and this is like the flooding once in 100 year, once in a 50 year, and once in a 10 year. Same way, this is for Mahanadi Delta. This is respectively Q10, Q50, and Q100. Each again, we can see we just applied some better visualization, like putting a set like Google Map kind of thing in there to make it better visualize for us which cell will be flooded and which will be fine. So all right. So what are some of the limitations that we have with our project? Now, apart from some of the common error that we can have, like in the digital elevation model here and there, the biggest problem that, as I mentioned, was there's no exact depth data that is openly available. So that we are calculating using a mathematical formula that can give a lot of variation from the real depth that is actually there. Second thing is, while we because I downloaded the data of the last 20 years to find my Q100. It's not ideal to use only 20 years data to get Q100, but because of each data set costing like 2 GB of the data. So the problem that I got is we cannot have data more than of 20 years. So Q100 is kind of extrapolated data, so it might be a little bit offset here and there. So we can get maybe rather than 20 years of data, we can get that 40 years of data and calculate a Q100 in a better way. Last thing is it's a small change, but let's consider a friction factor that is called Manning's friction factor. We consider it to be constant throughout because we also don't have any data set available for it. But for water flow, it does not make that big significant difference because friction factor don't contribute that much. So I think that can work. Yeah. So finally, I like to conclude with the stakeholders that we have. The first stakeholder is obviously the disaster management authorities. For example, NDRF, who needs the flooding region in the case of some climate hazard like flood or a cyclone or something. So in that, this can be really helpful. Then again, local communities can be really helpful because they know what are going to the flood prone region where they want to maybe make their house, or how the then urban planning also, like municipality, sorry, where they have to focus more on this. And then lastly, of course, agriculture, because the water layer can literally kill the crops because of because it hinders the oxygen supply to the roots of the plants. So it can destroy the crops. So it will be helpful. It can be helpful for the farmers also. And of course, climate change adaptation, because the water discharge is directly dependent on the glacier, how glacier melts in most of the cases. So the water discharge variation that we'll got uh, can also indicate what is the condition of the glaciers that is currently like what's the condition of the glacier right now. So yeah, thank you for. I like to conclude here.
Thank you, Devraj. Can we now have Mehesvi from IIT Bombay?
Yeah, good evening, everyone. I'm Mahasri and said today I'll be presenting my bleaching risk modeling. The objective of this project was to develop a machine learning framework capable of predicting coral bleaching risk while investigating how different environmental and spatial factors contribute to bleaching. Coral reefs. Coral reefs support nearly 25% of all marine species, making them one of the most important marine ecosystems. However, monitoring reefs still relies heavily on field surveys where divers physically visit individual reef sites. This process is expensive, time consuming, and cannot be carried out frequently across thousands of reefs worldwide. At the same time, satellites continuously measure environmental variables such as sea surface temperature, depth, turbidity, and wind conditions. The idea behind this project is simple. If we can use this readily available environmental data to predict bleaching before it occurs, conservation agencies can prioritize high-risk reefs and take timely action instead of responding after the damage has already been done. Moreover, reliable predictions of reef health can also support marine biologists in studying ecosystem changes, biodiversity loss, and the impact of bleaching on species that depend on coral reefs. This is the motivation behind this work. While while several bleaching prediction models already exist, this work focused on exploring a few additional aspects. First, instead of relying only on the conventional thermal indicators such as SST and DHW, I incorporated multiple environmental variables into the prediction framework. Second, I investigated whether geographic location itself contributes to bleaching prediction. Third, I systematically evaluated the contribution of every environmental and spatial feature rather than simply reporting prediction accuracy. Finally, I explored whether historical bleaching observations could be used to represent reef resilience and improve future prediction. To investigate these questions, the project followed the following methodology. The study began with a review of existing literature to identify commonly used data sets, important environmental variables, and suitable machine learning approaches. I first established a baseline model using only the conventional thermal indicators SST and DHW. This served as a reference model against which all subsequent improvements were evaluated. Next, I expanded the baseline model by incorporating additional environmental variables such as depth, wind speed, turbidity, cyclone frequency, and distance to shore. Uh, After improving the environmental model, I investigated whether geographic location itself influences bleaching prediction. Instead of directly using latitude and longitude, I converted them into three-dimensional Cartesian coordinates, x, y, z, which provide a better representation of location on the Earth's surface, which enables calculating a better calculation of distance. Finally, I've trained the model using observations from 1997 to 2015, computed the residual errors, and used a KNN-based spatial interpolation to estimate a historical resilience proxy, which was then evaluated on the 2016 to 2020 test set. Now, coming to the outcomes of these additions, the experiments show a clear progression in prediction performance. The baseline model using only SST and DHW achieved an R-square of approximately 0.48. After incorporating the additional environmental variables, the predicted accuracy improved significantly to an R-square of approximately 0.69, including spatial information further increased the performance to an R-square of approximately 0.71, indicating that geographic location provides meaningful predictive information beyond environmental variables. Future importance analysis showed that DHW, depth, SST, and cyclone frequency were among the most influential predictors. However, the proposed historical resilience framework did not improve predictive performance under the current experimental setup. To conclude, this work demonstrates that coral reef bleaching prediction can be significantly improved by moving beyond conventional thermal indicators and incorporating multiple environmental factors. The results also show that geographic location contributes meaningful predictive information, suggesting that regional or sea-specific models may further improve prediction accuracy. Although the proposed historical resilience framework did not improve predictive performance, it highlights the complexity of modeling reef resilience and suggests that richer reef-specific ecological information may be required. Overall, this work provides an interpretable machine learning framework that not only improves prediction accuracy, but also offers insights into the relative importance of different bleaching drivers. Thank you, everyone.
Thanks, Mahesvi. Next, can we have Ashish Kumar Jha from IIT Kanpur to make his presentation?
Hi everyone. I am Ashish Kumar Jha, student of IIT Kanpur, currently in fourth year of my study, pursuing BTech in Mechanical Engineering. So currently as an intern at MRC, I was working on the project which is coral reef bleaching future prediction for the Indian Oceanic region. So first of all, introduction to this project and why do we need this project specifically. So, I mean, we have different models, predictive model for different reef systems across the world. Like, let's say there are a prediction model for Great Barrier Reef, which is the largest reef system in the world. And we have a different prediction model for, let's say, I mean, the reefs that are present in Pacific Ocean, but not a particular model that is trying to incorporate different features and try to predict it accurately for the Indian Oceanic region. So we are trying to cover that up. So what is our approach is here that we would be using three factors here, and we would see why those three factors only. So in my model, we are using sea surface temperature, then OLR, which stands for outgoing long wave radiation, and sea surface height. And why only these three features is sea surface temperature is directly, which gives you the information about the temperature of the sea level, and which is directly related with the bleaching part, I mean, which is the most influential factor, I mean. But there are certain other factors as well. And one of the important one is OLR, which stands for outgoing long wave radiation, that tells you the radiation that the sea surface is emitting. But due to the greenhouse effect, those radiation are being captured by the CO2 gases present in the atmosphere and redirected to the ocean surface. So that is causing a major effect to the bleaching. And then the sea surface height, which gives us the information about the oceanic current. So, I mean, different in the sea surface height at two different regions, we can get the information about the oceanic current and their flow, which gives us the information about the flow of nutrients and the flow of temperature. So that could play a major role in predicting the bleaching here. So our methodology is, first of all, getting these three data sets. And after getting these three data set, we are trying to see, then there is a need to get the Y variable. The Y variable can be all the chances of bleaching in the past that has been occurred in the Indian Oceanic region, not the particular years only, but the region. So, I mean, we are not trying to predict the year only. We are also trying to predict the region, the particular region that is at most risk. So, and after we have predicted something, then we need to evaluate it. So for that, we are using equitable threat score, something that is very common in prediction of these type of area. So we are using ETS. And when we have predicted something, we need to see what are the factors that are contributing the most and what are the factors that are, I mean, seeing how the factors are contributing really. So we use SHAP, that tells you the information about how different factors are contributing here. So how telling you about this data set. So I have to maintain the uniformity of this data set, I have downloaded the 20 years of all of them, starting from 1993 all the way to 2023. And I have selected the monthly data set, one data point for each month. And for SST, I have downloaded it from NOAA, same for OLR, and for sea surface height, the source is CMEMS. So after getting all of this data set, we are trying to build our multi-factor risk model. But the major problem here was getting the proper data set for the bleaching history in the past. So there have been studies which has been done for the Indian Oceanic, which shows that there has been bleaching in different years, but not a particular data set that we can directly use in our model. So the major problem was that I'm still trying to figure that out, what we can use instead of that, because we are not trying to figure out the year, but the main goal was trying to predict something like a resolution, let's say a 5 kilometer of resolution, in which we can give it a risk score, how how much risky it is for that region, the bleaching part. So after we have, actually build this model, who are the stakeholders for this project? So first of all, the policymakers who are directly representing the climate change, the climate risk of India and Indian oceans in the let's say international conferences. Uh, they can get this data, and it can be a proof to present at those conferences. Then there are some future researcher who can use this data set. Then they are, let's say there is a travel industry who directly rely on seeing if they are setting up their infrastructure around some reef system, then that has to be a guaranteed that it's not going to be bleached in the next upcoming 3 to 4 years. So that's going to be a useful information for them. So to conclude my project, this project establishes an environmental data foundation required for Indian Oceanic region particularly, and it acts as an early warning sign for them, translating a validated Great Barrier Reef methodology. And that they have been incorporated. We are trying to do the same, but with a different methodology here. So thank you so much, everyone. That's all about my project.
Thank you, Ashish, for your presentation. Next, can we have Pranav Ashok Mahitkar from IIT Madras to make his presentation?
Good evening, everyone. So, I'm Pranav Ashok Mahitkar, a third-year mechanical engineering student at IIT Madras. And the project that I'm working on is wind and rain-driven ambient noise layer for the Indian Ocean region. So, the goal of the project is to build the natural acoustic baseline for the IOR, or in other words, you can say that we are building a model by which we can calculate how much noise is generated in the ocean due to wind or rainfall. So, as region is one of the world's strategically and ecologically critical bodies of water, yet its underwater soundscape remains poorly understood. Most regional ocean planning treats underwater noise as purely anthropogenic, focusing entirely on commercial shipping. The natural noise score, that is, the noise generated due to wind and rainfall, is entirely unmapped for this region. So, and without this baseline, it is impossible to assess how much extra noise the vessel traffic adds and where the biologically sensitive quiet zone exists. So, the outcome of this project is a 3D ambient noise layer with a 12-month climatology delivered as separate wind and rain modules and then integrated into the MSP toolkit. There are various stakeholders and beneficiaries for this project. The naval and defense forces can use this for submarine operations, mine countermeasures, and maritime domain awareness activities in the IOR. Hydrographic organization can use this for climate products and navigational safety assessment. Conservational bodies and e-NGOs can use this to identify seasonally shifting acoustic quiet zones, which are critical for noise-sensitive marine species. Marine spatial planners can use this as a plug-and-play ambient noise layer for the MSP toolkit. And this project can also be used for research and scientific purposes, as well as shipping and port management. So the unique features of this project is first, this is the first IOR-specific natural noise baseline. Second is dual source separation. The wind and the rain are modeled independently, so the user can analyze each source separately. Third is monsoon-aware seasonal climatology. Fourth is these models are based on equations from research papers by renowned scientists like Hildebrandt and Newton. And fifth is plug-and-play integration into the MSP toolkit. So the methodology project is step one was literature review. We went through a number of research papers to gather the required knowledge and the necessary equations. Step two was the collection of multi-data set acquisition, uh, like ERA5 reanalysis for the speed of wind and NASA GPM for the precipitation rate, etc. Step three was the spatio-temporal alignment. So we have interpolated all the data set to a common 0.25 degree master grid. Step fourth is acoustic modeling. For the wind layer, we are using Hildebrandt's empirical equation. And for the rain layer, we are using Newton's empirical equation. And the step five was to generate a 12-month climatology and to capture effects of southwest and northeast monsoon, and then integrate this into the MSP tool. So this is the equation that we are using for the wind model, and this is the equations that we're using for the rain. So we have integrated both of these models, the wind and the rain, into the MSP toolkit. And the planner can toggle a wind noise or rain noise layer and then adjust the month, depth, and frequency and generate an interactive noise map. These are some of the results from the wind model. So on the left side, as you can see, the noise generated due to wind in the month of July is considerably higher than the other months. And this is due to the presence of southwest monsoon. Some other results are this. This is the comparison between the noise generated by the wind in the ocean in the northeast monsoon season and the southwest monsoon season at a frequency of 500 hertz and a depth of 100 meters. This is the result for the rain model, a comparison between noise generated by rain in the southwest monsoon season and the northeast monsoon season. And this is the July snapshot. If you look at this image, you will see that this represents the noise generated due to rainfall in the month of July at 5 kilohertz frequency and 0 meters depth, which means the surface of the ocean. The user can generate these kind of noise maps for wind as well as for rain for different months at different frequency and at different depths. And by these noise maps, we can have different or very useful insights regarding the ocean. And in the conclusion, I would like to highlight that this project provides value on three aspects: the planning value, the ecological value, and the strategic value. By combining the raw weather data into the living acoustic map of the Indian Ocean, which will enable smarter, science-based, and sustainable ocean governance. That is it from my side. Thank you.
Thank you, Pranav. So with Pranav, we culminate our presentations of group one. Moving on to the second group is going to focus on the presentations are going to focus on the topic called sediment management, which is critical component of sustainable riverine and coastal ecosystem governance. The first presentation will be delivered by Sagar Yadav from IIT Delhi. Sagar, over to you.
Good evening, everyone. I am Sagar. I am pursuing mechanical engineering at IIT Delhi. So my project at MRC was calculation of sediment bearing pressure. My approach will be Bayer's toll geoacoustic approach for this. Okay. So currently there are two research approaches for the calculation of sediment bearing pressure. One is classical, which is accurate, that is the CPT testing method, but it is invasive to the sediment and is not scalable over the large areas. Another approach is the acoustic approach, which is scalable, but it is not accurate enough so that to get a defensible number or could be utilized in the production requirements. So sediment bearing pressure will be required for anything, if any offshore infrastructure is built on the seawater, any amphibious or logistical trafficability is needed. So, and also it will be helpful for designing military strategies if we know, like, we know the sediment bearing pressure for Indian Ocean region properly. Next is what my methodology, which I will be presenting, includes, and why is it different from others. So my goal was to pursuing the acoustic approach only, but increasing its accuracy such that it can be usable. So basically, for that, I included every environmental factor that would be affecting the sediment bearing pressure. Basically, seawater density and viscosity, which will be derived from the temperature, salinity, and depth. Also, sediments are always a mixture of many different components. So I tried to model the mixture properties as well. And also, there is another property that if carbonate percentage greater increases the 50%, then different methodology is used for the calculation of sediment bearing pressure. So my approach also takes account of for that. And then the Hardin-Strain model calculates the dry frame pressure. And for the effective vertical stress, I'll be using the Athis compaction profile to calculate to integrate the vertical stress depending on the porosity of the seawater at that level. And finally, as a safety factor, we have two methods: Terzaghi-Mayarov basic method and Tezcan-Kesely methods for the calculation of sediment bearing pressure. And these are two independent methods. We'll be calculating by both of these with appropriate safety of factors, and we'll be using the one which have minimum value to ensure better accuracy. So here comes the methodology part. Basically, firstly, I will be taking the input, the maximum grain diameter, fines fraction, mineral mixture type, and the temperature, salinity, and depth of the seawater. Also, for the foundation case, we'll be using the foundation characteristics as well. Then comes the calculation of the fluid properties and grain solid. We will be using the Voigt-reduced Hill method for mixed mineral moduli. Then then comes the calculation of the sigma b, that is effective vertical stress, using the Athis compaction profile, and for the calculation of the moduli for the dry frame of the mixture of the sediments using the Hardin-Strain method. Then comes the main pipeline Bart-Stoll method, which converts the dry frame into the wet frame and gives us the shear velocity and V shear velocity and V compressor velocity VP. So the Tezcan-Kesely method takes Vs and gives the sediment bearing pressure. But in case of the Terzaghi method, we have another procedure, that is we need to calculate the stiffness factor, which is undrained shear stress SU, which it is calculated directly from the shear velocity that is coming out of the Bart-Stoll model. It is governed by a power law, the factors A and B. These are the constants which need to be calibrated by the site specific data. So my model also includes to be accurate, my model also includes that we need some CPT data, and such that by curve fitting we get the A and B parameters. And by the Thevenin fines and Bolton's method, we calculate the internal friction angle. Now these two values go to the Terzaghi-Mayarov basic method, and in my calculation part right now, I have assumed factor of safety here for 3, and in the Tezcan method as factor of safety for 4. So these two methods will be used for the calculation of sediment bearing pressure. So this is final methodology. I have one example of the calculation part where the mixture is mixed sand with 25% fines and water depth is 50 meter, and the calculation of sediment bearing pressure will be below 5 meter the seafloor. And the footing width is 2 cross 2 cross 2 cross 2 cross 1. So firstly there is a linear bend, that is we are not accounting the mixture of the sediments. mixture properties of the sediments. So it comes out to 77.7. For the after using my pipeline, the Terzaghi-Meyrov comes out to 65.9, and the Tesgan-Kesely comes out to 46.5. So we will be using the minimum one, that is 46.5. So seeing both the results, if we did not work on this and use the linear method, there will be a high certainty of failure at 77.7 kilopascal, since the appropriate sediment bearing pressure will be 46.5. That's why the accuracy is important for the sediment bearing pressure, and my approach includes the accuracy part as well. Nextly, for conclusion, the approach calculates the sediment bearing pressure from grains to completely to the end, and also gives us accurate enough answers to be used by the industrial works as well. Also, for the shallow Indian Ocean region, this can be easily configured with the some amount of safety data and calibration of the A and B parameters. That's all. Thank you from my side.
Thank you. Can we now have Aryan Singh from IIT Delhi?
So, good morning, good afternoon, everyone. My name is Aryan Singh, and I am a BTech student from IIT Delhi. So, today I will present my project using satellite images to estimate the suspended sediment concentration in the Ujjaini Reservoir. I had used Sentinel-2 satellite and QGIS software to do so. So, let me start with why this topic is important. Sediment in water reduces water quality. It also reduces how much water a reservoir can store. So Ujjaini Reservoir gets pollution from areas like Pune. Normally, people check water quality by collecting samples by hand, but this is slow, costly, and covers very few locations. So what I had used satellite like Sentinel-2 to solve this problem. It gives us images which is free and is available at every 5 days of interval, which at a very good resolution of 10 meter. So the location which I am studying is located at Bhim River in Solapur district, Maharashtra. It is one of the largest reservoirs in Maharashtra. It is used for irrigation, drinking water, and all many purposes. So because of these many uses and because it faces pollution, it is important to monitor its health. Here is what makes my project different. First, I did not use just one index. I had used multiple index, namely NDWI, NDTI, and two band ratios. And second, I had compared pre-monsoon image and post-monsoon image to see how sediment actually changed. Third, my whole method uses free data and free software, so anyone can repeat this work at no cost. Now let me explain my method. So I had used Sentinel-2 images, one from 10th May before the monsoon and one from 20th October after the monsoon. I used 4 bands, blue, green, red, and near infrared. I merged the satellites in I merged the satellite tiles in QGIS, then clipped them to the reservoir boundary, and then prepared them for analysis. So my full workflow has mainly 6 steps. The first one was data acquisition. The second one was tile merging. The third one was clipping, then index generation, analysis, and then the final was SSC mapping. So I calculated 4 indices for the both of the dates, and so NDWI was basically used to separate water from land, and then NDTI tells about the turbidity index. So I had included that also, and then the both of the ratios were used to because it displays the change in the color with the change in the concentration of sediment. So here are the actual Sentinel-2 images which I extracted from the near infrared band across the 3 dates. Water absorbs near infrared strongly, so clear water looks dark, which can be seen in the image. And sediment-rich water reflects a bit more, so it looks lighter. So these are the raw images which I used to calculate the spectral band ratios. And these are my actual results. this slide basically compares the 10th May image to the 20th October image, which is a pre and the post monsoon side by side. So firstly, NDWI, the water mass visually the same before and after the monsoon. That is expected because NDWI basically tracks the presence of water and not the concentration. So NDWI was used to basically to mask the water from the land. Secondly, I had used NDTI. This number also remains almost same, and it shows that it should have shown some changes in the turbidity, but it does not actually respond here. So these were the two indexes, and this slide also compares the two band ratios. Same again for the same two dates. Rate to green ratio rose by 63%, and rate to NI ratio nearly doubled, with a 96% rise in it. So out of all four indices I tested, rate to NI ratio was clearly the most sensitive to the rise in sediment after the monsoon. This chart summarizes the comparison directly. Red INR shows the strongest jump, followed by red green. NDTI is left out because it almost remains the same, maybe because of some noise. So my key result is that band ratios, especially rate to NR, track the sediment increase far better than the two indices built specifically to measure turbidity or water. And my method has some limitations also because it needed the images. I had to look for a cloud-free image, and we don't have the field data for the validation purpose. And 10-meter resolution cannot show very small features in the map. So we can, in future, we can also add the, if we get the field data, then we can validate our result and then apply some regression models. And then we can also use it for long-term monitoring systems. To conclude, Sentinel-2 images with pre-QGIS tools gives us a low-cost way to monitor sediment in Nirdhwani Reservoir. Comparing four indices instead of just one gives a more reliable results, and showed the rate to NR ratio was the best among all four. And comparing pre-monsoon and post-monsoon images clearly shows how sediment changes across the season. So, yeah, that is all from my side. Thank you, everyone.
Thanks, Aryan. With this, we move to the third group of presentations where the students are going to make presentations on the topic of marine biofouling. And we have the first presenter who is Varun Malviya from IIT Kanpur.
Myself, Varun Malviya, and I'm currently pursuing BTech in Material Science and Engineering from IIT Kanpur. I'm going to introduce you to my project, Clean Hull RL, mentored by Suchit. This is an academic research project focused on creating a deep reinforcement learning AI to improve how we schedule ship maintenance. Specifically, this AI-driven framework is designed to optimize fleet deployment in the Andaman and Nicobar Islands. Let's start with the baseline problem. The Andaman Sea features warm and nutrient-rich waters, usually between 27 and 30 degrees Celsius. This environment triggers aggressive marine biofouling, rapid biological growth on ship hulls. The growth creates severe physical drag, forcing engines to work harder and burn millions in excess fuel. To make the matter worse, there is a massive 1,200-kilometer geographic bottleneck. Ships must travel all the way to mainland, dry dock just to get clean. Now, to solve this, my framework focuses on three main opportunities. First is dynamic scheduling. Instead of guessing based on fixed calendar, I use a data-driven LLM model to schedule maintenance. Second is localized oceanographic data. Rather than relying on generic global estimate, I integrated actual satellite data like sea temperature and salinity to calculate approx fouling. Now, third is very important, that is mathematical trade-off. my model constantly calculates the optimal balance between the compounding daily cost of wasted fuel versus the massive lump sum cost of the 1200-kilometer dry rock transit. Now, after collecting this localized ocean data, I have analyzed the data, which led to a major discovery shown on the right. Initially, based on existing literature, I plan to use an additive model, assuming that as water gets warmer, fouling simply increases. But my data proved otherwise. The extreme heat and rich nutrients in the Andaman Sea multiply the biological growth like compound interest. Seeing this aggressive correlation, I rejected the additive approach and upgraded my framework to a multiplicative model using the Q10 biological formula. But upgrading the math was only the first step. I also had to redesign the reward function. My first reward, based only on fuel savings, made the agent clean the hull over 40 times. Adding a large maintenance penalty caused the opposite. It almost never cleaned. I even tried a Goldilocks reward, meaning a bonus for an ideal number of cleanings, but that only rewarded a proxy instead of the true economic. Finally, what I've done is that I moved these operational limits into the environment as hard constraints, keeping the reward focused on real economic outcomes. To systematically solve this problem, I followed a three-phase methodology: analyze, quantify, and re-architect. First, I needed to analyze the system. Initially, my model was failing. By testing, the agent was finding shortcuts and gaming the simulation instead of optimizing for the true economic objective. Second, I had to quantify the real world impact. I analyzed the real economics of hull fouling and found some mathematical insight. That is, fuel costs don't just increase, they don't just increase linearly, they increase quadratically as the cleaning gap widens, making delayed maintenance exponentially expensive. Finally, I re-architect the RL environment. Instead of just using generic penalties, I enforce strict operational rules like realistic maintenance windows and a maximum of 8 dockings as hard constraints. I then use potential-based reward shaping, which force the model to learn and actually solve the problem. This brings us to the final results, the actual financial and strategic impact of this framework. To prove that my model works, I first needed a bulletproof baseline, the correct human standard operating procedure. I didn't just estimate this. By applying the fluid dynamic equation to the traditional fixed calendar approach, I have calculated the true operational cost. Now, running a SARU class baseline under human protocols costs approximately 52.63 million annually in compounded fuel and transit penalty. Then I let my model take command. Instead of waiting for random calendar dates, the model dynamically schedules maintenance just before that multiplicative drag spirals out of control. The final model policy converged on 8 precisely timed cleaning, successfully dropping the total annual cost to 49.25 million. This is a mathematically validated saving of 6.4% per year. Ultimately, through this research, I have found a highly effective alternative to traditional rigs. This AI-driven framework demonstrates a new approach that effectively balances economic efficiency with uninterrupted fleet readiness. Now, to conclude, this project successfully achieved its goal of transforming hull cleaning from a fixed maintenance schedule into an automated system. The model produced schedules that were both operationally feasible and economically superior. More importantly, this is not limited to a single vessel. This architecture is designed to scale by integrating live oceanographic API feeds and extending to multiple vessel classes, making Clean Hull RL a strong foundation for future operations. That's all from my side. Thank you.
Thanks, Varun. Next, we'll move on to Lavina Goyal from IIT Kanpur.
Yeah, so good evening, everyone. I am Lavina Goyal from the Department of Biological Sciences and Bioengineering at IIT Kanpur. I am currently a fourth-year undergraduate. Today, I'll be presenting my internship work titled Biofilm Maturity Framework, a conceptual model for understanding recruitment competency in tropical marine biofilms. So during the literature review, I found that the biofilm maturity is usually inferred using only one parameter at a time. Researchers commonly use indicators such as immersion time, biomass, thickness, or surface coverage. However, these measures often produce inconsistent results because of biofilms of the same age can behave very differently depending on their microbial composition and ecological development. There is no unified definition of biofilm maturity, making it difficult to compare studies or predict recruitment. This revealed an opportunity to develop a multidimensional framework that integrates physical, structural, biological, and functional indicators into a single conceptual model. So the existing studies have already explored many individual aspects of biofilms, including microbial succession, EPS production, quorum sensing, and larval settlement. The limitation is that these factors are usually studied independently. My contribution was therefore not to introduce new biological parameters, but to integrate existing knowledge into a unified ecological framework. The framework defines biofilm maturity as a multidimensional process rather than simply the age of a biofilm. It also introduces the concept of recruitment competency, describing the ability of a mature biofilm to support successful larval settlement. So the framework was developed through a structured literature-based methodology. I first performed an extensive review of marine biofilm ecology, microbial succession, EPS production, quorum sensing, and recruitment biology. Next, I identified research gaps in existing maturity assessment methods. I then focused on studies from the Indian Ocean region to capture characteristics specific to tropical marine environments. Key indicators reported across these studies were extracted and grouped into 4 interconnected dimensions. These are the physical indicators, the structural indicators, the biological indicators, and the functional indicators. Finally, each dimension was supported using published evidence, resulting in the conceptual framework presented here. So the main outcome of this work is the proposed biofilm maturity framework. Rather than viewing maturity as a function of time, the framework describes biofilm development as a continuous ecological process. Physical indicators describe the extent of colonization. Structural indicators represent the organization of biofilm matrix. Biological indicators capture microbial succession and community complexity. Finally, the functional indicators determine whether the biofilm can actively influence larval settlement. When these dimensions collectively reach sufficient maturity, the biofilm becomes recruitment competent, increasing the likelihood of successful macrofouling establishment. This framework also provides a foundation for future quantitative maturity indices. So in conclusion, this work identifies an important gap in the current biofilm maturity assessment. The proposed framework integrates multiple biological processes into a single conceptual model, providing a common language for comparing studies across different marine environments. Although it is currently conceptual, it establishes a foundation for future experimental validation and the development of predictive maturity indices capable of estimating recruitment potential. Thank you.
Thanks, Lavina. With this, we move to the final technical session of today's webinar. So the final technical session focuses on fisheries and aquaculture, which is one of the key societal dimensions of the UDA framework. The first presenter is Shivam Gawande from IIT Bombay.
Good evening, everyone. I am Shivam Gawande. I am from IIT Bombay. During my internship at Maritime Research Centre, I worked on the problem of detecting and characterizing small artisanal fishing fleets operating beyond AIS coverage in the Indian EEZ. Since direct validation of non-IIS vessels is challenging, I developed a VIRS-based satellite detection framework and validated it using Maharashtra's annual monsoon fishing ban as a natural experiment. So India's exclusive economic zone covers approximately 2.4 million square kilometers, but our current maritime monitoring relies heavily on AIS. The challenge is that most artisanal fishing boats either do not carry AIS or are not required to transmit their location. This creates a significant blind spot for maritime security, fishery management, and blue economy planning. The objective of my work was to investigate whether freely available NOAA VIRS boat detection data could complement AIS by monitoring vessel activity independently of the vessel broadcast. So, among the available technologies such as SAR, RF, and optical imagery, I selected VIRS boat detection because it provides publicly available nighttime vessel detections independent of the AIS. To evaluate the methodology, I used Maharashtra's annual fishing ban as a proof of concept. If the framework is reliable, vessel detection should consistently decrease during the ban period and recover once the ban is lifted. This provides a real-world validation scenario for assessing the performance of the framework. To address this problem, so to address this problem, I first developed and first extracted Maharashtra's coastal district from the geo boundaries and administrative data set. Since Raigad district boundary extend inland, I manually processed it so that only its coastal contributed to the study area. Next, I dissolved all the coastal districts into a single coastline, projected the geometry, generated a 12 nautical mile offshore buffer. Using this study area, I processed 16 monthly NOAA VRS boat detection rasters covering May to August. Each raster was clipped and masked to a closure polygon, after which I extracted the total detections. Finally, I implemented the modified VIRS closure index, which normalizes every month detections against that year's May baseline. This removes inter-annual validations due to fleet size or sensor differences and enable meaningful comparison over years. So these were the results that were obtained. Validation was one of the most important components of this work. First, I statistically validated the MVCI using one sample t-test. The reduction observed during June, July, and August were all statistically significant with p-values below 0.01. I also compared the June with July and July with August to evaluate progression of fishing activity throughout the closure period. To test the robustness of the framework, I normalized detection by raster composite length because different VRS products represented between 15 and 31 days. This changed the result by only 1 or 2 percentage point, indicating that the conclusions were not influenced by different observation period. So then I compared the total detections with active detections, active pixels, and obtained a correlation coefficient of 0.096. Uh, the limitations of this work, most importantly, is that only 4 years of where the data was analyzed, and majorly it was not covered up to 12 years. And VRS detects only illuminated vessels and can be affected by cloud cover during the monsoon season. Therefore, it should not replace the AIS, but instead it should complement existing maritime surveillance, and in the future could be integrated with other technologies. So to conclude, the validated VRS-based framework for monitoring small fishing vessels beyond AIS coverage using Maharashtra's proof of concept, the framework consistently detected the statistically significant reductions in the vessel activity across 4 independent years. Uh, Although the demonstrated using masters, this framework has a potential to be extended to monitor small artisanal fishing fleets uh, using uh, potential to extend the monitor small artisanal fishing fleets across the Indian EZ and can serve as a valuable component to existing AIS-based maritime domain awareness systems. Thank you.
Thanks, Shivam. The next presenter is Shivang Gupta from IIT Delhi.
Good evening, and thanks for joining. My name is Shivang Gupta. I'm a research intern at MRC and a chemical engineering undergrad. Under the guidance of Ashwini sir, I've done this internship and worked on a problem that sounds impossible when you hear first, that India farms the ocean, but we cannot see that. So let me show what I mean by that. India is the world's second aquaculture producer, secondly only after to China. And more than half of the fish we eat now comes from the farming and not the wild catch. The government is pushing this hard enough through the Pradhan Mantri Sampada Yojana. And along with both our costs, you'll find fish cages, seaweed rafts, and that is a blooming blue economy sector. So the opportunity is real, and the question is, can we see it from the orbit? So here's the shocking part. The leading global mariculture map records India offshore mariculture areas effectively zero. And number two producer in the world, over 50% of our fish supply, zero on the map. And this gap hurts across four national domains. First is blue economy. Blue economy planning is no baseline. The environmental ministry has no footprint inventory. Maritime security does not know what structures are at the sea, and marine spatial planners can resolve conflicts they cannot see. So why this is the problem, and why we haven't done this solving it? So four structural reasons, and none of them are fixable just by launching a better satellite. First, our farms are too small. A typical 6-meter fish cage is smaller than the single 10-meter satellite pixel. The measurement is bigger than the object. So this is the first reason. Second is our skies are cloudy for months during the southwest monsoon, exactly when the optical sensors go blind. Third is our rivers are muddy. The Ganga, Godavari, Krishna, all of them confuses the brightness threshold tuned for the clear South China Sea. Fourth is global methods were calibrated on large, dense, and clean water Chinese and Korean farms and transferred that directly into India. So definitely they're going to report blank ocean. So this project builds India-specific framework around four principles. First is monsoon resilient. SAR radar is the primary sensor because radar sees through the cloud. SAR weighted optically only supports and verifies the data, inverting the global hierarchy. Small sensitive farms, temporal composting and texture analysis to pull the sub-pixel signals out of the noise, and critically validated locally against CMFRI Indian records and not just on the global statistical data. So what was the methodology? The pipeline runs entire in the Google Earth engine. 6 stages were defined. First is ingest a year of Sentinel-1 data, blend into a median composite to kill the passing noise, mask out land, threshold for bright structures on water, filter out stray pixels, and then measure area and cross-check with the optical data. So basically Sentinel-1 leads, Sentinel-2 supports, and CMFRI validates the data. I tested that 6-stage pipeline on the Konkan coast first. The pipeline returned a near zero real detection. Anything bright in open water turned out to be choppy waves on visual inspection. And now it seems like this is a failure, but this is not. This is the problem we reproduce. 6-meter case set down below the 10-meter pixel floor, and the null result is the finding here. Yeah, I mean, this is what I want to say. The null result is the finding there. I'm not mistaken. To prove this, that the pipeline is not broken and is working, and in the exact same code in the Mandapan in the Palk Bay region, a documented dense seaweed cluster in clear shallow water. and 28 sentinel images were obtained. The results were approximately 29 hectares detected on the Olicoda cluster zone, and CMFRI documents 1750 hectares across the whole district of villages. And so 29 hectares for one dense cluster fits that ratio, big enough to be real and like small enough to not to be seabed. The two results only mean something together. Konkan alone looks like a failure, and maybe Park Bay alone looks like a lucky win. But side by side, if we see and compare, that small farms are still invisible, big farms are detected, and both are being checked out as per the rule. And the Konkan null is genuine and under detection, not a broken method. India is not unmappable. It just needs the right method that verifies that. And being honest, like the limitation part was that, being honest, the 29 hectares probable number, not ground verified. Some clumps could still be boats or seabed. The year bin composite mixes growing and harvest seasons and sub-pixel which cages are still invisible with higher resolution commercials are. So this was just a validated proof of concept and not yet a national invent. The path from here seems like an engineering problem and not the invention problem. To the end, like from a global blind spot to a more mappable coastline, I think India specifics our framework like I've coded into and feel proven on two of the coast and ready to scale. That's the my project, and thank you.
Thanks, Shivang. We'll now have the last presentation of the day. But I'd like to call Samya Kumar from IIT Madras to make his presentation.
Yeah, so good afternoon, everyone. I'm Samya Kumar, a final year BTech student in Naval Architecture and Ocean Engineering at IIT Madras. During my internship at MRC, I've been working on the project titled Marine Heatwave Drivers, Predictability and Fisheries Impact in Bay of Bengal. The main objective of this work is to understand the major climate drivers responsible for a marine heatwave formation and to build a scientific framework that can be used for prediction. So why do we need to study the marine heat waves? So marine heat wave is the time frame when the sea surface temperature remains much warmer than normal for several days or even weeks. Over the last few decades, these events have become more frequent because of climate change. They affect marine ecosystems, coral reefs, fisheries, and even influence regional weather patterns such as monsoon. So the results of this work is useful for several groups. One of the major stakeholders is the fisheries and aquaculture sector. Marine heat waves can cause fish to migrate to cooler waters, change their distribution, and reduce fish availability in traditional fishing grounds. If these events can be predicted in advance, fisheries can better plan their operations, reduce economic losses, and also better plan their operations. Scientists can better plan understanding how marine heat waves develop, weather agencies can use these findings to improve forecasting. Government organizations can use them while planning climate adaptations and marine conservation strategies. So let me now briefly explain the methodology. So I started by collecting sea surface temperature and other oceanographic variables, climate indices such as Oceanic Nino Index, the Dipole Mode Index, and the Multivariate ENSO Index were also collected because they represent a large scale climate variability. After pre-processing the datasets, marine heat waves were detected using the Hobday definition. The detected events were then divided into North, Central, and South Bay of Bengal regions. The Bay of Bengal is not a homogeneous basin. The northern, central, and the southern regions have different oceanographic characteristics and are also influenced by different atmospheric processes. So therefore, analyzing the entire basin as a single region may hide important regional differences. I then performed several statistical analysis, including the frequency analysis, lag correlation, duration analysis, intensity analysis to understand the influence of climate drivers. Finally, the complete workflow was designed so that it can be extended into a machine learning framework for marine heat wave prediction. So now let's look at the major results obtained during the study. So first using 20 years of daily SST data, I identified a total of 117 marine heat waves between 2006 to 2025. They were divided into 49 events in the North Bay, 40 events in the Central Bay, and 28 events in the South Bay. I then studied the influence of ENSO on marine heatwave occurrence. The marine heatwaves in the South Bay were predominantly associated with the El Nino conditions, which were 15 events, unlike the North and Central Bay, where events were more evenly distributed. This means that more than half of the marine heatwaves in the South Bay were occurred during the El Nino conditions, meaning ENSO has a real influence on the marine heatwave occurrence in the South Bay. I then analyzed marine heatwave duration and intensity. The statistical analysis show no significant differences across El Nino, neutral, and La Nina conditions. This means ENSO mainly influences how frequently marine heatwave occur, but not how long they last or how intense they become. So around 80% of the marine heatwaves occur during weaker than normal wind conditions, suggesting that reduced wind mixing allows the ocean surface to retain more heat. So this slide shows the spatial evolution of two marine heatwave events observed during the study. The top row represents one of the longest marine heatwave, which lasted 81 days, while the bottom row represents one of the strongest marine heatwave, which reached a maximum intensity of 0.94 degrees centigrade above the climatological threshold. For both events, the three maps show the sea surface temperature anomaly at three different stages: before the event, during the event, and after the event. Before the marine heatwave begins, the warming is relatively weak and limited to small parts of the Bay of Bengal. During the event, the warm anomalies become much stronger and spread over a much larger area. The dark red colors indicate regions where the sea surface temperature is significantly higher than normal, clearly showing the peak of the marine heatwave. After the event ends, these warm anomalies gradually weaken and shrink, indicating the ocean is returning to its normal state. To conclude, this project helped establish a systematic and reproducible framework for studying the marine heatwave in the Bay of Bengal. Through this work, I was able to identify the major climate drivers influencing the marine heatwave occurrence and understand how their influence varies across different regions. Thank you all for your attention.
Thank you, Samyak. With this, we've concluded with all the presentations of the day. So these were the presentations that we have. And as we all know, the research flourishes through constructive dialogues and expert guidance. We are privileged to have with us an esteemed panel of experts who will share their observations and feedback. It is my honor to invite Rear Admiral Y.N. Jairatne, retired sir, who is a former chief hydrographer of Sri Lanka. Sir brings over 3 decades of distinguished experience in hydrography, maritime security, and ocean governance. He has played a pivotal role in strengthening Sri Lanka's hydrographic capabilities and advancing initiatives such as marine spatial data infrastructure. Following his retirement from the Navy, he has continued to serve the global maritime community as international consultant to the United Nations, contributing to areas including undersea cable, maritime intelligence, and ocean affairs. We are privileged to have him with us today and share his valuable insights and feedback. Sir, the floor is yours. So we're not able to hear you.
Admiral sir, you're not audible, sir. No, sir.
Sir.
You may probably...
Can you hear me now?
Yes, sir, yes. Thank you.
Okay. Right, now we are in line, right? Okay. Dr. Das, and I'm delighted that you got me into this. And at the beginning, let me congratulate each of the speakers, the young speakers. I'm impressed and I'm delighted to hear them. And it is impressive. 5 minutes is not enough. Yes, I know, but I can see the amount of thinking and rationale that has gone into your studies. That is impressive. And the kind of scientific thought process that has gone into each subject That's very impressive. And I am glad that these youngsters has gone so in detail into these affairs and bringing out their methodologies or their outcome and the kind of a thinking and the use of technology in hand. That's very remarkable. So bringing these youngsters into forums like this, Dr. Das, I must congratulate you, and I'm congratulate the MRC for arranging these forums. So these youngsters are giving me a lot of assurance that the future is bright. I'm glad. So let me, with that opening remark, come to the sequence. I may not go into each one's details because that will be too much, I guess. And it doesn't mean that if your speaker's name is not mentioned that you have been undermined. It is not the case. And each one of you have impressed me, and I'm very much hopeful about our future with people like you and in the next generation thinking on this way regarding our maritime space. So coming to the MSP, Marine Spatial Planning, Devraj Singh, this is marvelous. See, the river mouth estuaries are very dynamic and prone to siltation and sedimentation and variation, so dynamic. So how you brought out your assessment is and your design methodologies, I would say it's remarkable. And I think the 20 years of data is good enough for mapping. One thing is the what we observe on the ground. When we put things into the map, there will be always resolutions and about the scale. The scale hide many finer details that in actual terms what our eyeballs see on the ground. So actual and the mapping have two different projections. So that's good enough, I would say. Then coming to second speaker, Mahasri, coral reef monitoring. Uh, I that is a good analysis and methodology. I would say that although you didn't had any outcome of your the study, but the methodology you followed up is very logical, I would say. And coming to Ashish Kumar, it is your one pointed out the lack of regional data. You have to depend on some basically the NOAA. Everybody is depending on these the American the NOAA because that's the systematic collection of data. Now this showcase why we should be stepping on our regional databases where we just like the NOAA system we share them and use them for wider usage among ourselves. And I'm glad that you use those things. And that's why in my early commencement I said about the kind of the available tools and the sources that you have used. Amazing. You have gone into all the corners and very happy about that. Then come to Pranav Ashok, your rain and wave noise mapping. That's another brilliant one, I would say. And I'm impressed with your assessment and how you have gone to the assessment based on this data. Something relatively new, noise and wave mapping. It is the noise and wave noise, rain and wave noise mapping is something relatively new, but it have a scope in the future with we go for detailed marine science, marine spatial planning requirements as we go along. Group 2, the sediment management. Sagar Yadav, scientific thought process that has gone into your study. That is brilliant, I would say. And what is your thinking is what caught my attention in your presentation. See, based on this modeling, what you have proposed, we can do much, I would say. Then come to Aryan Singh, the reservoir sediment, and this is a classic example of making things workable for our practical use. All the reservoirs are going, I would say already they are experienced in this thing. So your study with the Ujjain reservoir, the utilization I would say is very high, and I hope our policymakers will not make note of that. So I'm sure with the ground truthing, these things could get verified very in detail. But it's a good showcase of how much you can get it through these satellite imageries and working things for your own usage. Then marine biofouling, this very interesting thing. And so when Varun Malviya spoke about the Andaman Sea, the cost comparison, that's another good thinking, I would say, how you come up with this cost comparison. At the end of the day, people be looking at especially the policymakers will be looking at the cost comparison. I would share one of ours. In Hambantota Harbour, we use Sri Lanka Navy used to have the OPV class strategic reserve. What do you mean by strategic reserve? Is the 1 or 2 OPVs that are on standby to deploy on short notice. So we used to keep them in Hambantota Harbour. But ultimately, we found out that when they were deployed, they are losing speed by 3 or 4 knots. The reason is the biofouling, because the water is clear, water is clean, and sunlight penetration is high, good, and it make biofouling very conducive and expand. So you see, these things matters in naval, and this all matters in the commercial aspects also. And this, in once again, one part is a business itself also. Cleaning underwater is a business itself. So I am very much happy with your cost comparison. And Lavinia Goyal, so biofuel maturity, how you structured that whole model that is fascinating, and your infographic explanation, I would say, is remarkable. And then the fishery and aquaculture, Shivam, your artisan fisher monitoring, that's another aspect that well, I would say, other than the fishery monitors, even the coastal monitors, the maritime domain awareness will also have an interest on these things because of the usage. Then coming to the final, the Shivag, the fish farming, seaweed cultivation, I would say that's your another kind of brilliant thinking that has gone into that your under detection problem. So the reason the too small, sky cloudy, river muddy, wrong ocean, kind of give a different perspective, and why we should have our own systems for our coastlines in our MSP and in our blue economic planning. And coming to the last, Samyak, marine heat wave drivers, and it's another way. I'm sure you are must be monitoring these things at present, how things are happening right now in our ocean frontier. It will be propagating to land. And I'm glad about these youngsters covering up these things, and all are these IT campuses. And so it's a brilliant effort, and it is a very timely, and it's a foundation and investment for future. So thank you, Dr. Das, for bringing these youngsters to come and speak. And I'm delighted to hear you, and I'm delighted to know that you have done this kind of thing. Thank you.
Thank you so much, sir. Really appreciate your comments, sir. Thank you very much.
Thank you so much, Jairatne sir, for your kind remarks and for the feedback for each of the interns that we have with us today. We are honored to have you. Now we invite Dr. Hussain Rashid Hassan to the stage. He's the former Minister of Environment and former Minister of Fisheries, Agriculture and Marine Resources in the government of Maldives. Dr. Hassan is a distinguished leader and policy expert with extensive experience in environmental governance, sustainable fisheries, marine resource management, and climate resilience. Throughout his distinguished public service career, he has played a significant role in shaping the policies that promote the sustainable use of conservation of marine ecosystems while advancing blue economy agenda in the Maldives. His expertise is balancing environmental stewardship with socio-economic development that brings valuable regional perspective to today's discussion of the underwater domain awareness and sustainable maritime governance. So we are honored to have you with us today. The virtual floor is yours.
Thank you. Can you hear me now? Okay, Nish, thank you so much for giving that kind, introduction, and I'm honored to be here. I first of all thank Dr. Das for inviting me for this webinar, and he has been asking me to be part of this webinars he's presenting on his institute. But the last time I was not being able to take part, but this time I'm here. Anyway, it's an honor to be here. I wouldn't take really long time because previous speaker, our Admiral, Rear Admiral has actually spoken, I think, on behalf of me as well. I mean, these young scientists are remarkable, and I congratulate them for their well thought out research work. And I think we have seen research work elsewhere, but sometimes you don't really understand what the methodology really speaks about. But here it's different because the young scientists have actually developed the methodology in a coherent way and then got the data and tested, and then presented the data in a way that actually in a very simple manner, so that even non-scientists can understand. Non-scientists like myself can understand that. I'm afraid I'm not actually a scientist like you are. I'm a fisheries economist by profession. So I'm more interested in managing fisheries and fishery resources. And I speak more about managing the natural resources rather than looking into biotic and abiotic conditions of the ocean. So anyway, I must say I was impressed by some of these presentations. I must admit some of these presentations are actually the jargons, the technological concepts that presented is new to me even. Okay, but then I learned a lot as well, and I was very impressed by their presentation, and especially the way it is presented. Very simple, very short, but it is very easy to understand and digest. So I congratulate all of you for your very well presented research work. Okay, looking at, I want to actually highlight three particular points. One is in our region, I think it's not very common that people looking into ocean and finding out the problems that we have, and also how we may actually improve ocean governance and how we may get benefits from the oceanic resources that surrounds us. For instance, India is a large EEZ, and but they don't have a large tuna fisheries. They don't have a large tuna fisheries, and if you see other countries, European Union and Chinese and others are actually fishing in the Indian Ocean and getting the best, out of it, and they are deriving benefit from it. And the best the coastal countries are getting is some nominal resource rent in terms of excess fees. These are very small amounts. So I think it's about the time that we take the ocean resources seriously, management of it very seriously. Right now, the Indian Ocean Tuna Commission is the only body managing the tuna resources in the Indian Ocean, but other resources like squid and and other fishes are not really managed. They have been harvested and the stocks are being decimated. Okay, my point is, I'm very happy to note that India is actually developing the technology not only to go to space, to moon and Mars, but also looking into underwater. That actually will benefit our coastal communities immensely. So I think I'm very happy to note that. I've seen two Indian scientists going to tuna commissions and really speaking about technical things rather than management aspect of it. Okay, but I think India being one of the having the largest EEZ should actually take responsibility of managing these resources with other coastal countries as well. So that is very important. So when you speak about how to detect vessels, farms using the technology, these are very promising because one of the problems that we have in the Indian Ocean is actually illegal fishing. And that comes with a lot of other problems as well. Illegal fishing associated with the drug smuggling and the arms smuggling, all that related to that. So if we can detect easily the vessels without paying active fees for the vessel satellites, then that's a way to do that. But I know that also requires coordination and cooperation with other coastal countries. But the willingness is more important. I think I'm also very much interested to note that the El Nino, he associate heat waves are actually causing, havoc in the Indian Ocean. The human-induced climate change is a major problem, and countries like Maldives are especially suffering from this. And there's been questions about the very existence of Maldives. The sea level rise apparently, will increase, and our islands submerged one day. But the real problem is, what are we going to do about it, or what can we do? And but with the new knowledge, even Maldivians are now more optimistic that we can survive because we have learned how to build new islands. We have to learn how to cope with the increasing sea level rise, and we are learning actually new strategies how to cope with the increasing sea level rise. Similarly, the fisheries is changing in the Maldives too, because the heat waves, El Nino, La Nina impact over the years has actually shifted the fish aggregation patterns in the Indian Ocean. With a heat wave, the much valuable yellowfin tuna and big-eye tuna is moving downwards. That means with surface level, we can't catch them as we are catching before. But skipjack still forms schools at surface level, but then we have the Persenas catching that before we catch them using pole line. And detection and monitoring of fishing fleets are very important. So I'm very happy to note some of your young scientists have actually come up with new ideas that we can probably use. Vessel monitoring, VMS, is very expensive for our small fleets. AIS is not much of use because they can switch it off, and VMS can be done as well. But probably the secondary data that you have suggested, we can find out, more about the patterns of these illegal fisheries as well. So once again, I note that the new methodology is very useful. And also using the satellite, not only you can detect the fish farms, but also other features, relating to coastal erosion and changes in reef structures, and also livelihood patterns, agriculture, and all that can be detected, and measures can be implemented as a result of that. So I was very interested to know some of these new technology, new ideas that your young scientists have presented. And once again, I congratulate you. I'm really sorry that I was a bit late to join, but I've been hearing your presentation and making notes is that you went along. So I'm sure there'll be another opportunity to engage with you guys at a later stage. Thank you. Thank you very much.
Thank you so much, sir. Really appreciate your comments. Thank you.
Thank you so much, Dr. Hassan, for your kind remarks and for sharing your thoughts and perspective with all of us. As we come towards the close of today's program, it is my privilege to invite Ambassador Retired Sudhir T. Devre, sir. A member of the Indian Foreign Services, Ambassador Devre retired as the Secretary in the Ministry of External Affairs, Government of India, after an illustrious diplomatic career spanning more than 3 decades. He has represented India as ambassador to several countries, including Indonesia, Nepal, Morocco, and Papua New Guinea, and has made significant contributions to India's foreign policy and regional engagements. An accomplished author and respected commentator on international relations, Ambassador Devre continues to contribute to policy discourse on India's neighborhood, the Indo-Pacific, and maritime cooperations. We are deeply honored to have you with us, sir, for today's program, and the floor is yours.
Kindly unmute yourself, sir. Sir, you're muted, sir. Kindly unmute yourself, sir. Ambassador Devre, sir.
Sir, you're muted.
Shreya, you can just call sir and guide him again.
Yes, sir.
Our team is actively working with him, so we'll just probably in a minute or two, we'll be able to sort it out.
Dr. Das, can I ask how these youngsters were? Are they? How they were assigned with these topics? And
yes, sir. Yes, sir. Basically, we have this summer internship which has been going on with the top 5 IITs for the last 5 years. So it started with 300 applications. It went up to almost 1,000 applications, and these are only the BTech students who are.
Can I speak now? It's okay.
Yes, sir. Yes, sir. Please go ahead.
yeah.
Sir. Yes.
Okay. Well, sorry, there was some confusion about this muting, unmuting. I'm really grateful to Commander Das for organizing this, inviting our distinguished guests from Sri Lanka and Maldives, and having young scientists from prestigious IITs. Well, I think the presentations which they made, even for a layman like me, I'm a non-scientist in the company of all scientists, were very illuminating and must say very revealing. So I find them like new startups in the area of the maritime field, and they should be encouraged and promoted in that spirit. Well, MSP has been very much in the reckoning nowadays, much talked about issue. And I feel that just as we need land use planning, which has been going on for forever, we need ocean planning as well. And I think that need cannot be overemphasized. So whatever that takes, we need to do that. And I think the today's papers came to know some of the conclusions were drawn towards that. They need to be utilized. I don't know whether satellite imagery can be adequately used for MSP. MSP, I think, is basically in shallow waters, so there it can be easily utilized. That is something I don't know, but I think we need to look into various possibilities of MSP data, and I think the digitization which MRC has undertaken for MSP can be further expanded. Your whole UDA is based, I feel, on sonar technology. Sonar use is very important in that. Now, sonar, as one of the papers showed, the prevalence of sonar in due to shipping as well as due to waves and other movement of the animals, sea animals. These are two different things. My question is there any legal framework for regulating sonar sounds? Sonar, because sonar gives us the facility to know the movement of what movement inside this ocean. And we have today ISA, which goes into the seabed authority. There is a regulator. Now you have BBNJ for borders beyond the national jurisdiction. Something to do with the just as now considerable discussion on oil splits. How to regulate sonar? That could be one more, I think, point which can be thought of. There's a layman, I think, like that. In the Bay of Bengal, my own observation for many years has been that there has not been enough exploration or extraction for natural gas as well as hydrocarbons. And now, in the last 15-20 years, there has been sufficient development of technology which should enable, I think, greater exploration. In your papers also this afternoon, I find that there is now discussion going on about monitoring satellite based sedimentation. Now, basically, natural gas and hydrocarbons are found in sediment. So, is there any utilization of this new technology towards this end? This is a matter of considerable importance given the geopolitical importance that Bay of Bengal region is now acquiring. There are considerable opportunities in that area. Whereas we find that the level of development in terms of resource, resource utilization in Bay of Bengal has been limited. And how your techniques, UDA techniques, can be utilized, I think could be a very useful study. So I think today's webinar is really very important in the sense it has provided ideas for practical utilization of natural resources of the oceans. And when we talk of MSP or blue economy, that is the main objective. And therefore, I really congratulate you, Commander Das, and I would like to again felicitate all the young scholars and scientists on their very enterprising ideas and research. One point which Dr. Hassan from Maldives mentioned about illegal fishing, I think this is of great importance to India. And combined, I think, as he mentioned, with illegal or the drug smuggling or the arms drug smuggling, etc., how we can tackle this problem of illegal fisheries. India is a member. India is a member of the Tuna Commission, but as he pointed out, the illegal fisheries in Indian Ocean goes on unchecked, and countries which are far away from India, they are taking the advantage of that. So this is something, an area which again MRC can go into and some produce some studies on how to check and arrest illegal fishing. So thank you very much for inviting me and listen to all these interesting studies. Thank you.
Thank you so much, sir. Really appreciate. Sir, I will quickly not clarify, I mean, just add a couple of things. I mean, more than thanking everybody, Admiral Jairatne sir also asked this question. Sir, as we talk this summer, we had 36 interns working with us, and they're all from premier institutes in India. I mean, and multidisciplinary, as you can see. The top 5 IITs we had. Today's batch is basically the IIT students because the time of joining is different. So we have clubbed them because we cannot have too many presentations at the same time. So today was the IIT students. 3 days back on 15th, we had 17. BITS Pilani is another private institute, but a very well-known institute. So we had 17 students working with us from there, and they were physically with us and they presented to esteemed audience like yours. And also we have on the 9th of August, we have there is another institute in India called St. Stephen's, more known for its liberal arts faculty, economics, history, English literature. So we have 4 interns from there, and also our own research fellows who are working in the liberal arts domain. They'll also be presenting. So 9th, we have a presentation with them. So we are trying to populate the UDA framework, which all of you have seen before, and with each of those cubes, there are so many dimensions. I mean, if we talk about biofouling, you know how many dimensions of biofouling are there. If we talk about fisheries, there are how many dimensions. So they are trying to populate, and Sridhar's presentation at the beginning was we have just completed a MSP handbook, which is gone for publication with Springer Nature, that will be available for all of you very soon. But that is the policy side of it and more of the conceptual side of it. But the actual ground digital platform is being built by Sridhar, along with all these interns who are contributing to the various dimensions. And this process of internship, the applications come to us from January, and this has been an organic thing. We have not put any advertisement. It has been growing over the last 5 years. We get almost 1,000 applications from the top 5 IITs. We are not able to go to other IITs also because the numbers are too high. And I mean, the enthusiasm you can anyway see. from their presentation. The enthusiasm comes because we are trying to solve real world problems. They can associate, they can take ownership of a particular problem and now with our series contract with Springer Nature, we have a series contract on MRC series on underwater domain awareness. So their final report will also come out like an edited volume, which will be a chapter in one of those volumes. So we may have to segregate them into different sectors of different topics. And so one book may have about 10 chapters and we'll try to organize that. So that work is also, there's a lot of work that my team is doing. And the way we conduct this is, I mean, earlier it was me and Sridhar who used to directly interact, but now I have stepped back a bit because the research fellows, we have 10 research fellows looking at multiple dimensions. So they have far better knowledge on the subject than me, I admit that. So they are now driving, and I can see that apart from what I can think, because these mentors are working on that topic for at least 3 to 4 years. So they have, and they come from the same set of institutes, very bright young people, and much more actively involved. So they, under Sridhar's guidance, built the whole tech platform. And so it requires a lot more, and they are ably assisted by my engineering team. We have 5 engineers who are there full-time with us, who give them the support of the computational platform and various other support that is required, and they are working tirelessly with them to kind of build this whole thing. So I think I will, and also what Dr. Hussain said, I mean, these problems, I mean, the socio-economic problems, I mean, whether it is IUU fishing or livelihood challenges or anything that you say, narcotics, smuggling, piracy, maritime terrorism, they are all interconnected. I mean, I was discussing yesterday, there is an AI center which has been inaugurated in Pune. We are a founding member of that. So the challenge is that fishermen are being told to put transponders on the ship. I mean, a similar version of AIS. They are not interested because they are hardly a very small percentage of fishermen are actually doing fishing, because that doesn't give them enough return on investment. And so they don't want to be tied up, or they don't want to be monitored. So what more can we give? I mean, so we are trying to say that the potential fishing zone mapping, that can be a tool that is given additionally to them, rather than it is not just a monitoring tool, it is something that they can use practically, and that will help them finding fish, and then that will be more viable for them. So, I mean, I completely agree with Dr. Hussain on resource management in the Indian Ocean requires a very, and the Western models will not work in our waters. So that's something very important. And as far as MSP is concerned, sir, what we are trying to do is the modeling and simulation based MSP. What it does is that using satellite data, but of course with significant validation on the ground using acoustics and also on ground sampling, we will focus on building the model, and that model will allow you to give very dynamic understanding. I mean, if you try and put sensors and collect data, how often can you collect data, and how expensive will it be is one question. But with this AI driven model, you can predict what will be the performance in next 5 years, 10 years, and even the climate change impact can be addressed in that way. So that will give you much better policy inputs when we are formulating. And as you know, there are so many aspects of the maritime domain which are either over-regulated or not completely touched at all. So this will, I mean, the UDA framework as a framework will actually bring a lot of structure to this whole management of the underwater space or the entire water space, both in the freshwater and the marine space. So I think I'll stop there, sir. And I was extremely today. Ambassador Tariq Karim just messaged he could not. Ma'am somehow had a fall, so he had to withdraw at the last minute. But I mean, the way we had thought that ambassador from India, I mean, who has a larger dimension, but you, sir, you have been in Indonesia and you've seen island countries. Tariq Karim, sir, has looked at the freshwater ecosystem very closely, and he's very passionately looking at the whole Brahmaputra basin. Admiral, sir, has been a practitioner, but he writes a lot on the strategic dimension. And of course, Dr. Hussain, who's a subject matter expert, plus he's looked at policy at a very highest level. And Maldives and Sri Lanka are probably one of the critical components. I mean, critical tropical island countries. I mean, so I mean, they have seen it all. So I'm extremely grateful to all of you for joining us, sir. And on behalf of the, so I think I'm happy on 4 fronts. I mean, one is the way the projects have been formulated, I think our mentors have done a great job. Sridhar, great effort by you and the entire team. The interns have done a fabulous job in kind of putting the vision together. Third, we had the fantastic panel both the times. I mean, we had a previous presentation also, and today again we had such a, I mean, the best team globally panel that we could have had. And also we are able to showcase capability. I mean, I'm not an official spokesman for the government of India, but I think India as a nation has a significant talent and depth that we can provide to our neighbors in the region and globally. So thank you so much, sir. Really appreciate all of you joining us. Thank you.
Thank you.
Thank you, everyone.
Thank you so much. Special congratulations to all the interns once again. Thank you.
Thank you.
Thank you.
Shreya,
Thank you. Are we finished?
Yes, sir. San, thank you so much. Yes, sir, we are finished.
Thank you. Thank you.
Thank you, everyone. Thank you, sir. Thank you.
Thank you.
Shreya and others, well done. Good job.
Thank you, sir.
Everybody, all interns, good presentation. Thank you so much. Nishtha, very well managed. Thank you so much.